This tutorial is presented in view of J.J. Thomson's experiment to find the charge-to-mass ratio of an electron. The setup of the experiment is like this. A cathode ray tube is like this. It has a cathode here and an anode over here. The region between the cathode and anode has gas at very low pressure. When a very high voltage is applied between them, the gas is ionized. The negative particles that are formed after ionization of the gas are attracted towards the anode. These negatively charged particles were proved to be nothing but electrons and were called cathode rays. These rays were sharpened to a beam by making a slit in the anode and another slit over here in this metal plate which was connected to the earth. At the end of the tube is a large sphere which is coated by some phosphorescent material such that the beam after striking over here create a bright spot. A scale is provided over here to measure the deflection of the beam. When there is no electrical or magnetic field, the beam travels in a straight line and there is no deflection. The beam over here passes between two parallel aluminum plates. When they are connected to a battery, the beam experiences an electric field in this direction and experiences a force in the opposite direction. The magnitude of this force is given by Fe equal to EE, where E is the magnitude of electrical field and small e is the quantity of charge of an electron. When a magnet is kept here, the beam experiences a magnetic field in this direction, and the direction of motion of the charged particle is this. According to the Fleming's left-hand rule, the negatively charged particle experiences a force in this direction. The magnitude of force is given by Fh equal to EVH, where Fh is the force experienced by the charge in the magnetic field. E is the quantity of charge, V is the velocity, and H is the magnitude of magnetic field applied. Firstly, both electrical and magnetic fields are applied simultaneously. They are adjusted in such a manner that these two forces cancel out each other. This is achieved when there is zero deflection of the beam. At this stage, Fe equal to Fh, or E into E equal to E into V into H, or V equal to E divided by H. Next, the magnet is removed such that the force on the electron is only due to electric field. In this situation, there is a force Fe equal to EE acting along this direction. Let it be Y direction, but no force along this direction, which is assumed to be X direction. Thus the problem is the same as that of a projectile in a gravitational field. In the X direction there is no force. The electron moves with a constant velocity where V equal to E divided by H. Thus distance travelled is X equal to Vt, which is equal to Et divided by H. Let this be equation number 1. In Y direction, there is a force Fe equal to Ee and an acceleration which is equal to Fe divided by m, which is equal to E into E divided by m. Therefore, Y equal to half At square, where A is the acceleration. Therefore, Y equal to half E by m t square. Now we get t equal to x into h divided by e from 1. Substituting in this equation, we get y equal to e by 2m x h by e whole square, which implies e by m equal to 2ye divided by x square h square. Now in this equation, the magnitude of electric field, the magnitude of magnetic field, y and x are known quantities. From the experimental results, we get E divided by M equal to 1.7588196 into 10 to the power of 11 coulombs per kg.